The Great Red Spot on Jupiter is a storm that has outlived empires, civilizations, and perhaps, one day, even the Macarena. Its winds reach 268 miles per hour, and according to confirmed observations, this atmospheric beast has been raging for over 190 years. To put that in perspective, the average storm on Earth lasts about a week. If a human lived proportionally as long as this storm, they'd be celebrating their 750,000th birthday. At that point, we'd comfortably call them immortal and probably ask a few follow-up questions. This storm is also ridiculously huge. At roughly 10,000 miles across, it's about the same diameter as Earth itself. Imagine if a hurricane on our planet was the size of the entire planet. That's not a local weather disaster. That's when meteorologists would just shrug and say, I guess the storm wins. In this video, you'll learn what powers this endless fury, how deep it reaches beneath Jupiter's clouds, what these monster winds would actually do on Earth, and why this legendary storm might be slowly starving itself to death. The Great Red Spot is a vast anticyclone, a high-pressure vortex where air circulates around a high-pressure center rather than rushing inward like Earth's hurricanes. Think of it as Jupiter's way of showing off, creating the atmospheric equivalent of a cosmic pinwheel that refuses to stop spinning. The spot's outer winds exceed 268 miles per hour, and the feature today is roughly 1 Earth in diameter, about 10,000 miles across. A century ago, it measured 2 or 3 times that width. Apparently, even immortal storms aren't immune to shrinkage with age. But here's the first physics puzzle. On Earth, storms die when they run into friction from land masses. It's like a cosmic brake pedal that brings even the mightiest hurricane to a halt. Jupiter, however, has no solid continents to scrape away momentum. It's essentially one giant ball of gas, which is why we call it a gas giant. The clues were there the whole time. The planet also radiates internal heat from its core, which fuels deep convection, the vertical motion that replenishes storm energy. Finally, the spot is sandwiched between strong east-west jet streams that keep it locked in place like a cosmic vice. Those 3 facts, no land friction, internal heat, and jet confinement, explain how a vortex can persist far longer on Jupiter than on Earth. It's basically the perfect recipe for an unstoppable weather monster. Everything changed when NASA's Juno spacecraft arrived in 2016, like a cosmic detective with really fancy instruments. Juno's gravity and microwave instruments revealed the spot reaches well below the visible clouds. The measurements are staggering. This storm extends at least 200 kilometers deep into Jupiter's atmosphere, with estimates reaching up to 500 kilometers in some analyses. To put this in perspective, Earth's deepest hurricanes rarely extend more than 10 miles vertically. The Great Red Spot is essentially a 3-dimensional tower of rotating gas that's 20 to 50 times deeper than anything we see on our planet. For comparison, if Earth storms were the height of a hamburger, the Great Red Spot would be the height of a large adult man, and it would happily eat a burger-sized storm for dinner if it got too close. More on that later. Recent Hubble observations have captured something that sounds like it came from a science fiction movie. The spot literally pulses and changes shape over time periods of months. The oval shape, brightness, and outer wind speeds cycle together, like Jupiter's atmosphere is doing some kind of slow-motion cosmic breathing exercise. Amy Simon from NASA described it perfectly. It's jiggling like a bowl of gelatin. As the storm accelerates and decelerates, it pushes against the windy jet streams to the north and south, like a sandwich where the slices of bread are forced to bulge out when there's too much filling in the middle. One question astronomers often hear is refreshingly simple. Why is the Great Red Spot red? The truth is, we don't know for sure, but recent discoveries are providing clues. Laboratory experiments and modeling suggest the color comes from photochemical reactions in the upper atmosphere. When ultraviolet light from the sun hits ammonia and other trace chemicals, it creates reddish or brownish compounds. Think of it like photochemical smog on Earth, but on a colossal scale and with better PR. Recent studies using advanced spectroscopy detected phosphine gas within the storm, which could be altered by sunlight into chromophores, molecules that give color. The exact mix is still debated, but what we do know is that the uppermost haze particles appear red, while deeper layers are likely whiter or more neutral. So the Great Red Spot is essentially a massive storm wrapped in a thin veil of photochemically stained aerosols, like Jupiter applied blush and got a little heavy-handed with it. Now for the numbers that will change how you think about wind and possibly make you grateful for Earth's comparatively reasonable weather. To compare Jupiter winds with Earth winds, we use dynamic pressure, which is the measure of kinetic pressure from moving air. The formula is beautifully simple. Q equals 1/2 times density times velocity squared. Here are our assumptions for full transparency. Jupiter's cloud top density is approximately 0.16 kilograms per cubic meter, while Earth's sea level density is 1.225 kilograms per cubic meter. Jupiter's atmosphere here is about 7.7 times thinner than Earth's, but the Great Red Spot's speeds are so extreme that they still produce devastating forces. Let's run the calculations for the spot's current maximum winds of 432 kilometers per hour. This creates a dynamic pressure of 1,152 pascals. To produce the same force on Earth, you'd need winds of only 156 kilometers per hour. That's a Category 2 hurricane not even the worst Earth can throw at us. Let's see what these forces would do to different objects. For an average adult human standing in 432 kilometers per hour Jupiter winds, the aerodynamic drag force would be about 970 newtons. That's a little more than their body weight. You'd be lifted off your feet and carried away like a leaf in a Jupiter. For a small car, the drag force would be around 760 to 1,650 depending on what angle it hits. Not enough to lift the vehicle, but more than sufficient to overcome tire friction and send it sliding sideways across pavement like a rather expensive hockey puck. For loose structures like signs or roofing, the forces become truly destructive. A typical section of metal roofing would experience about 2,950 newtons of force. That's 12 times its own weight. These objects would be torn free and hurled through the air with tremendous kinetic energy, turning your neighborhood into a very dangerous game of dodgeball. Dodge house, I guess. The Great Red Spot doesn't exist in isolation. It's the apex predator in Jupiter's complex storm ecosystem, like the T-Rex of weather patterns. Recent Juno observations have revealed that Jupiter's atmosphere is teeming with dozens of smaller anticyclones and cyclones, each battling for territory and energy in an eternal atmospheric competition that doesn't have sports betting yet. Consider Red Jr. Officially known as Oval BA, a smaller reddish storm that formed in 2000 when 3 white ovals decided to merge together like some kind of meteorological boy band. This storm, about half the size of Earth, has been steadily growing stronger and redder over the past 2 decades. When Red Jr. and the Great Red Spot pass each other every 2 years, it's like watching titans clash in slow motion. If titans were made of spinning gas and could level continents. At Jupiter's poles, Juno discovered something that sounds like it was designed by a mathematician with OCD. Geometric patterns of cyclones locked in perfect formation. At the North Pole, 8 storms surround one central cyclone in an octagonal pattern, while the South Pole features 5 storms in a pentagonal arrangement. These polar cyclones, each the size of major continents, have maintained their formations for years, creating what scientists describe as impossible meteorological geometry. Apparently, Jupiter's storms are more organized than your IKEA fjellbow. The most fascinating discovery is how these storms interact through what researchers call storm cannibalism. Smaller vortices that wander too close to larger ones don't just get absorbed, they get shredded apart, their energy and momentum transferred to the victor. It's like a cosmic food chain where storms literally feed on each other to survive, except instead of survival of the fittest, it's survival of the spinniest. The Great Red Spot is shrinking rapidly. It's lost about 2/3 of its width since the 1800s and continues contracting by roughly 580 miles per year. That's like losing the width of Texas every 3 years, which is genuinely impressive even by cosmic standards. Groundbreaking 2024 research from Yale University discovered the cause. The storm literally feeds on smaller vortices. Computer simulations showed that when smaller storms wander too close, the Great Red Spot absorbs them, growing stronger in the process, like the apex predator of weather systems. But as Jupiter's smaller storms have become less frequent, the Great Red Spot has begun starving, causing it to shrink. The predator has slowly exhausted its food supply. The very mechanism that kept it alive for centuries might now be causing its demise. Even immortal storms, it turns out, aren't immune to the consequences of their own success. There's also a new wrinkle to the story. A stunning 2024 discovery has rewritten the Great Red Spot's biography. Scientists analyzing historical observations found that the current storm is likely not the same one Giovanni Cassini observed in 1665. The original permanent spot disappeared around 1713, and our current Great Red Spot appeared in the historical record after 1830, meaning we have over 190 years of confirmed observations of this particular storm. This means we're actually watching the second act of a centuries-long atmospheric drama, like a sequel that's been running for nearly 2 centuries. And it raises a chilling question. If one Great Red Spot can disappear, what's to stop this one from vanishing too? Scientists have identified 3 possible futures for the Great Red Spot, and they range from reasonably optimistic to cosmically dramatic. First, it could stabilize at a smaller size and continue for centuries more, the diet and exercise approach to storm longevity. Second, it could shatter into multiple smaller storms, each spinning off to terrorize different parts of Jupiter. Third, and most dramatically, it could dissipate entirely within the next 20 to 30 years, closing the book on one of the solar system's longest-running weather shows. The key factor is shape. As the storm shrinks, it's becoming more circular, and circular storms are far less stable than oval ones. It's like the difference between a well-balanced spinning top and a coin trying to maintain a perfect spin. One of these things is going to wobble and fall over eventually. NASA's Rick Cosentino warns the next 5 to 10 years could be very interesting from a dynamical point of view. We could see rapid changes in the storm's physical appearance and behavior, which is science speak for hold on to your hats, things are about to get weird. The Great Red Spot serves as humanity's most powerful laboratory for atmospheric physics, like having a weather experiment that's been running for nearly 2 centuries with increasingly sophisticated data collection. Its longevity, depth, and dynamic behavior test vortex stability theories under conditions impossible to reproduce on Earth, unless we're willing to wait several hundred years and don't mind potentially destroying the planet in the process. The research revealing how the storm feeds on smaller vortices has direct applications to Earth's climate. Similar processes help sustain heat domes and blocking patterns that can cause extreme weather events, from deadly heat waves to prolonged droughts. So understanding Jupiter's monster storm actually helps us predict when Earth's comparatively tiny storms might ruin our weekend barbecue plans. The Great Red Spot represents nature at its most extreme, a storm so powerful it defies our everyday understanding of weather, yet governed by the same physics that drives clouds across our own sky. Whether it survives another century or fragments into cosmic memory, it has already taught us that the universe operates on scales both beautiful and terrifying, and occasionally has a sense of humor about the whole thing. You can actually see this wonder with a modest telescope from your backyard, which is amazing when you think about it. Time your observation for a spot transit across Jupiter's central meridian. With a 4 to 6 inch telescope and moderate magnification, the spot appears as a pale, brick-colored oval. Add a green or blue filter to boost contrast, and you'll be looking at winds that could literally blow you off the face of the Earth from a safe 400 million miles away. Thank you for joining me in exploring one of the solar system's most incredible phenomena. For more mind-blowing discoveries about the natural forces that govern our cosmos, make sure to subscribe and stay tuned.